So in 2019, there is a customer service center and they wanted to assess its performance, and they looked at a Likert scale. 1 is bad or awful, 5 great, amazing, whatnot. And the distribution for that particular year happens to be this, for 1 through 5, and N was 795. So they introduced a training program to make sure that the agents perform better in 2020, and they claim that it is effective. So this year, we collected a sample, and the sample gave these counts. And our objective is to verify if the training program is effective or not. Now, there is another test that one may want to use. What is the other test that one can use? But if you use it, would it be right? Huh? So one may say, well, I could just take the average of this and average of that, compare the two averages, and say, oh, yeah, effective, not effective. So you may say a two-sample test, independent two-sample test might work, but it's not going to work well because the counts are discrete, right? The scores are discrete. For that to work, we want a normal population, we need continuous data. We cannot use a two-sample dependent test or matched pair test because there is no matched pair here. Does that make sense? We are looking at different people. So the test of choice here should be a goodness of fit test. So the null and the alternative, what is the null? The null is that the fit that we had in 2019 is going to fit with 2020, yes?
So they're not the same 5 people that are being sampled?
No, these are scores.
Sorry, they're what?
Scores. 1, 2, 3.
Oh.
Yeah, those are the
sorry.
scores.
Bit
Yeah.
of a brain fart there. I got you.
Yeah.
Thank
So
you.
that they're not the same people. Yes.
So wait, are the 0.3 and 0.21, 0.9, are those frequencies? or-
Probabilities.
Probabilities.
Well, we're about to find frequencies. So our objective is to determine if the training program was effective or not. The reason why I brought those two things up, because you may read this statement and immediately think, oh, we have to do a matched pair test because we're trying to measure the effectiveness of the treatment. It's not true. That's not what we're trying to do here. What we're trying to do is, if this fit matches that fit. Good? Okay. I should say distribution, that's the formal word to use. The 2020 distribution is the same as the 2019 distribution. The alternative is that the 2020 distribution is not the same as the 2019 distribution. Now, which would indicate that the treatment is effective? The alternative would indicate that the training program is effective. If we don't find a word to word the alternative, then the training program is not effective. Are we clear so far? So, why is that the case? If that distribution did not change at all, then the training program did nothing, right? If that distribution if the new distribution is leaning more toward 5 and less toward 1, 2, and 3, then it was effective. It was more toward 1, 2, and 3 and less toward 4 and 5, then it actually made it worse, right? So we will see what happens. So alpha is 0.05, which would imply the probability in rejecting, the probability of error in rejecting the null under the given null that we have assumed has to be 0.05 or less. Next, we have to look at the data to get the observed frequencies and the expected frequencies, the O's and the E's. So, which would be the observed and which is the expected? Would the 2019 data be the expected, or would the 2020 data be expected?
2019 data.
2019 would be the expected distribution, because this is what we expect to see, right? That is our reference. This is what we observed. Does that make sense? So we're expecting this, so that would be the observed. The most common mistake that people would make here is to write the expected frequencies as you see here as 0.3, 0.21, 0.19, 0.15, and 0.15. That is incorrect. Those are probabilities. How do we find the expected frequencies?
Multiply by
Multiply by n. Do you have a question?
Yes, so will the expected frequencies always be in decimal form?
No.
Okay.
The last time we did it, we computed the expected frequency. So if it is a probability, you just multiply by the sample size. So we have to multiply each of them by 795. What is 0.3 times 795? Okay.
166.9.
What? What is it?
166.95.
166.95.
151.05.
151.05.
119.25.
The last one.
Same.
Oh, yeah. Never mind. So this was what we had in 2019, and this is what we have observed in 2020. Do you think that we sort of did better in 2020? No? Okay. So here's all the way up to 238. So, let's do the expected first. The expected for 1 is 238, probably right over there. For 2, it is 166. That's probably right there. For 3, it's 151, very close. And for 4, it's 119.25. And for 5, it's the same. I'm putting dotted lines because you can't connect them with the solid line because these are discrete lines. So that is the expected distribution. Now we go and look at the observed values. So we have 140, 212, 254, 161, and 89. So if you were a decision maker, what would you say? Is it better? Is the training program effective? You know, if you're the manager, you may say, hey, look, it went up and it's great. But okay, mathematically that is true, it went up and all, but if I'm your supervisor, I may turn around and say, hey look, it's less over there and it's different over there. We actually performed better in 2019 and at a scale of 5, but at a scale of 1, 2019 did poorly, so here 2019 was awful, but 2020 is better. But 2019 here was at a value of 3. 2020, we have more people. So there is a chance that the program is better, but we want to establish from a statistical standpoint if the differences you see are in fact meaningful. Does that make sense? So the next step is to find the test statistic. I showed you how to find the sum of all O minus E squared divided by E last time. So put all O values in list 1, E values in list 2, and compute the statistic form. We don't want to do the sum manually, it'll take forever, especially if the sample is large. So we know O's are in list 1 and E's are in list 2. So second 1 minus second 2 squared divided by second 2. L1 minus L2 squared divided by L2. That would be O minus E squared divided by E. And we can save these values by hitting the store button to list 3, second 3. Enter. And if I go back, just that, the values are all stored up there. We have 40.68, 12.156, and so forth. And if we did one variable statistics of list 3, we'll get a whole bunch of things, but all we want is the sum of each of the values in list 3, which is in the second line, 145.29. Does that make sense? Yes?
How did you get it to go to L3 again?
So second 3. Oh, how do you make it to go there? So let's see if I can. Second 1 is L1 minus second 2 L2 squared divided by second 2, which is the expected value, STO button right above the on button. Click that, it'll point, give an arrow, and say second 3.
Thank you.
I typed that equation into the header on list 3, like we were discussing last class, and I got the same values as you.
Oh, like on the header, yeah.
Yeah, so if anybody has the TI 84 plus, you can do it that way also.
So what Anthony is suggesting is you can go up to the header and change as L1 minus L2 squared divided by L2 right there. And you can edit it over here and say second 1 minus second 2 squared divided by second 2. That'll give you the same answer. It's a matter of choice.
So when we stored the L1 minus L2 squared for L2 and saved that as L3 and immediately put it in here?
Yes. So we've got a value of 145.294. So here is the key for you to, guess the answer even before you start the problem. Remember earlier in the semester I said if the p-value is really, really low, you will reject the null. In a similar manner, if the chi-square value is significantly large, then by default the p-value is going to be really, really low. Now here we got 145.229. That is a large chi-square value. The chances are we are going to reject the null, and we are going to see that the p-value is very low. So the first method is the critical value method. What type of distribution is a chi-squared? It is a right cube distribution. It's going to look like that. And you cannot have a negative value whatsoever for the test statistic. The area in the right tail is 0.25. And we have to find that critical value. And that critical value is chi-squared 1 minus alpha comma degrees of freedom, which is k minus 1 in this case. K is 5, the number of levels we have. 5 minus 1 is 4. So we need to find chi-squared 0.95 comma 4. If you have a TI 83, 84, 84 plus calculator, it doesn't have a function to find the chi-squared critical value. So what should we use to find the critical value? The chart. So the table here summarizes critical values based on the area in the upper tail. But if you look at other textbooks or if you Google something, they might actually base it on the lower tail, so you've got to be careful. In our case, what is the area in the upper tail, which is why I drew the area over here. That area is 0.25. So you go to the column 0.05, which is right over there, and the degrees of freedom here is 5 minus 1, because we have 5 levels, minus 1 we get 4, so 4. The critical value is 9.4 pp. Does that make sense? Okay. So from the table, the critical value happens to be 9.488. So the critical value is over here. Where is the test statistic? 145.29. So probably way over there, right? Is it in the rejection region? Absolutely. So mind you, statistics can only tell you if something is significantly different or not. You've got to use a bit of your mind to identify if the training program is effective, if you should invest more in it. So based on the picture that we see, this fit, that distribution and the distribution that we expected, they are clearly different, and statistics concluded the same. We just have to determine if it is effective. Do you believe that it is effective? The observed values. So the probability of getting 2, 3, and 4 rating is higher than the probability of getting 1 and 5. So we had the chances of getting 2, 3, 4 in the year 2019 to be lower. But in 2020, we saw more of 2, more customers gave a 2, more customers gave a rating of 3, more customers gave a rating of 4, but 1 and 5, not so much. If someone asked you, should we give this training program another go for 1 more year, what would you say? Would you be willing to give that choice? I probably will, because it seems to give some improvement. And whatever improvement that we see is statistically different, so it is worth the investment. Does that make sense? Okay. The next method is p-value. The chi-square test here is always a right-tail test. So the p-value here would always be the area above the test statistic. So 9.488 is over there, and the area about 9.488 is only about 0.25%. The test statistic is way over here. How much area do you expect below that test statistic, or about that test statistic? Close to nothing, but it has to be extremely small. We will see. What did we use last time to find this? We use chi-squared CDF. (145.29) all the way up to infinity, comma k-1, which is the degrees of freedom. Plug it in the calculator and tell me what you get. 2.08 times 10 raised negative 30. That is extremely tiny, right? That's like the size of, a neutron or something. So this is approximately 0. So under the null, and given the data that we had observed, the chances that we could go wrong in rejecting the null is 0%. Knowing that, could we comfortably reject the null? The probability of us going wrong is 0%, so we can actually reject the null comfortably. We already have the data in list 1 and list, yes?
I know we used the table for the critical value, but can you do that on the calculator? If so, what function?
We cannot, because your calculator doesn't have that function.
Okay.
So we need to have that table for the exam. So if we press start, go over to tests, scroll down, okay, what would you go to? the chi-square GOF test, not the chi-square test, chi-square GOF. This froze on me, so that time. So put it in there and you should get the same answer. Critical value would be 145.29 and the p-value is 2.08 times 10 raised negative. That's it. Yes? Good? Awesome.
So what are we putting in for degrees of freedom? Is that 794 or is that 4?
4.
Okay, thanks.
So